Okay. So here we go. Size of molecules influences boiling point. All right. Alyssa, what kind of intermolecular forces are we talking about when we say that the size of molecule influences the boiling point here?
The London forces.
The London forces, that's right. And we can see how for neon, argon, krypton, xenon, there's a clear trend. Even the molecular gases, fluorine, chlorine, bromine, and iodine. And the trend is also a favorite of chemists, this trend from fluorine up to iodine, because fluorine and chlorine are gases at room temperature, whereas bromine is a liquid at room temperature, and iodine is a solid at room temperature. So this is a good trend and often a question that tests will ask because of the clear indication of the increase of intermolecular forces when you think about these compounds, or these atoms, sorry, molecular in nature, fluorine, chlorine, bromine, and iodine, just moving down the periodic table changes their state from gas to solid. Okay, so a good example, good model. Okay. So, compressibility. Gases can be compressed because you can think of them as atoms with lots of space between them. And so if you just keep packing gases in, you can get a lot of gas into a fixed container, for example. But the same thing is not true for liquids. Liquids, you don't have a lot of compressibility. Essentially, they're incompressible, essentially. All right. Some other things that intermolecular forces bring to the equation, or teach us about. One of them is what we call packing effects. Another thing is called surface tension. If I have a surface of atoms, like if this is glass, for example, then when another molecule hits the surface, that molecule will spread out on that surface according to the amount of intermolecular forces that it can kind of have in common with the surface. So let's talk about this a little bit. If I have a surface of glass, that is going to be essentially some silicon and oxygen, and it's not just SiO2, whoops, it's long, making mistakes, it's long chains or polymers of silicon and oxygen, all right? And what do you think? What kind of intermolecular forces are we talking about here, Landon?
London dispersion forces.
Definitely London dispersion forces, but these silicon-oxygen bonds also have a significant degree of polarity associated with them. So you can have some dipole-dipole forces. So that means when something like water comes and hits a glass surface, the water will have a significant amount of interactions that can occur here. You're going to have some good dipole-dipole interactions between water and a surface of silicon oxide or glass. Okay? Now, remember how when we talk about a graduated cylinder and we want to be able to determine how much water is in there, when we fill up a graduated cylinder that's made of glass, we get this kind of a shape. Anybody remember what we call that? Alyssa, do you remember what we call that?
I can't remember the technical name.
It's called a meniscus. And we always measure the bottom of the meniscus. That's the only thing we've been taught in class so far. But now we have an explanation for why that water crawls up the edge of the glass like that. And it's because of the surface tension that exists between water and the glass. Okay? If you fill a glass graduated cylinder with a compound that doesn't have dipole-dipole opportunities, you won't see that climbing. In fact, you might see the opposite effect, where, for example, if I used a hydrophobic compound like oil, it would try to resist contact with the glass. All right? It's been a long time, but when I was first a car owner, windshields were not as technical as they are nowadays, and water on windshields was kind of a big deal. It would get on the windshield, it wouldn't get wiped away as well as you'd like it to, and it was just because of the intermolecular forces. But now they'll put a layer, a surface on that windshield that will protect. So if you do have silicon oxide here, right, silicon and oxygen, that is a surface that will kind of allow other molecules that can dipole-dipole interact with it, a nice surface. But if you put some sort of a surface on top of there, a plastic surface, for example, that is mostly carbon and hydrogen, whoops, carbon, 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 right? This surface here, if I put just a little bit of wax or material on top of it, how will that change how my water molecule will want to wet or apply to that surface? What do you think, Taiwan? How will that change? Water, we said, likes to bind to glass surfaces because they both have similar types of intermolecular attractions. But if we put a layer of wax or some sort of hydrocarbon on the surface, how is that going to change how water will like to interact with this surface? Any ideas? That's right. So now the water can't interact with the silicon. It's going to have to interact with this carbon hydrogen. Is water going to be able to interact well with that carbon hydrogen, Taiwan? No, it's not. What kind of intermolecular interactions does water like to interact with, Harry?
London and hydrogen.
Well, it prefers hydrogen bonding or dipole-dipole, right? Its last choice would be London forces. And this surface here, what kind of interactions is it going to be able to interact with? Just a carbon-hydrogen surface. What is it going to want to interact with?
That's not polar, is it?
No. It's carbon-hydrogen. It's non-polar, right? So all it's going to want to do is interact with London forces. Therefore, if you get a drop of this water on here, the water is going to beat up and try to minimize the amount of interaction with this surface. On the glass surface, the water is going to try to spread out as much as it can to interact with this glass as much as it can. But if you have your layer on it, it's going to beat up, and then it's easier to remove off of the glass surface. So that's a property called surface tension or wettability. All right. In fact, here's an interesting video.
Molecules at the surface of a liquid experience unbalanced molecular forces. Since they are on the boundary, the molecules are attracted from inside.
Let's see, is this video not going to work for us?
Experience.
Let me look it up on YouTube really quickly here so we can see it.
Here's work.
Let's try it out. I can't cry on command, but I'm going to take some water, drinking water, put it in my eye just as if I was crying. Let's see what happens. Okay, so nice and stable for you here. Here we go. So, just as if I started crying, my eye is full of tears. But you can see it just forms a ball on my eye. In fact, I can put more water in. And so if you keep crying, you just end up with a bigger and bigger ball of water in your eye. Until eventually it crosses across your nose and gets into your other eye, or evaporates, or maybe spreads over your cheek, or you grab a towel and dry it up. So yes, I've gotten things in my eye. Your eyes will definitely cry in space, but the big difference is tears don't fall.
All right, so why is that? Why is it that in space, tears don't fall off your face?
Unbalanced.
Whoops.
Techme from B-Town, Ontario asked, is it challenging to brush your teeth in space
Whoops,
without
what's going
getting
on here? Hold on just a second.
toothpaste up your nose from weightlessness? Well, let's talk about how.
Okay, there we go. All right, so here we are. Okay, so why is that? What's going on there? Any ideas, Brielle?
Is it because of the surface tension, they just keep like sticking to each other, but there's no gravity to like pull it down, so it just like keeps forming a bigger and bigger ball of tears?
That's right. That's right. A compound with strong surface tension like water won't be, even if you shake it very much, the momentum's not enough to kind of break it apart easily enough. And so without gravity to help that breaking those molecules apart from each other, it'll just keep into a ball like that. Okay, very good. Viscosity is another property that intermolecular interactions influence. Viscosity. And viscosity, you can think of how fast a material, usually it's a liquid, will flow. How fast a liquid will flow. So, for example, honey, we say, is very viscous. Honey is very viscous. Water is less viscous than honey. Compounds like alcohol are actually less viscous than water. All right. So the higher the intermolecular forces are between molecules, the stronger those are, then the greater the viscosity in the compound. Okay. Wetting. We won't go over wetting, but it's basically the same thing. And here you can see a good picture of our drops of water on a surface of glass. Here it is, drawn for us nicely. Water spreads out over that surface very well. But when there's a layer of some sort of hydrocarbon in the middle, the water tends to ball up because now the surface tension becomes stronger than the intermolecular interaction between the water and that layer that's in between the silicon oxide. Okay. Very good. Now, solubility. Solubility. We've talked about solubility rules before, and solubility refers to the ability of a compound to dissolve into a solution, and generally it's water that we're talking about, a solvent of some sort like water. And solubility depends on, again, intermolecular forces. So if a compound has similar intermolecular forces as another compound, those two compounds will either, you could say, dissolve each other, or we'll say they are miscible. Miscible. Miscible is the word that we use when you're talking about two liquids, right? and you're just mixing them together, and you're not making a solution, you're just kind of making a mixture. But will they mix together? And we say that their compounds are miscible if they will mix together. And they'll be miscible if they have the same types of intermolecular interactions. All right. Now, some of you might know what a molecule of oil looks like. Some of you might not. But we should know, based on our knowledge of what happens when you mix oil and water, what kind of intermolecular forces oil has to mix with itself or with neighbors. Is it Sarah's turn? I think it's Sarah's turn. What do you think, Sarah? What kinds of intermolecular forces do you think oil has?
So it does not mix very well with water, so it probably does not have hydrogen bonding forces.
Okay, so it's not going to have hydrogen bonding forces because it doesn't mix well with water, and we know that water likes hydrogen bonding. Very good. And that probably also means that oil doesn't have what? What's another one that it probably doesn't have, Sarah?
Dipole.
That's right. Dipole. Very good. So no dipole here. Hydrogen bonding. So oil really only has London forces or van der Waals interactions. Okay? And for that reason, that's why you get oil and water separating if you try to put them in the same container. Very good. Let me draw you a molecule of oil, okay? What generally we think of when we think of oils, all right? This is what it looks like. You have a carbon bound to another carbon, bound to another carbon, 3 carbons. These carbons are bound to oxygens, and these oxygens are bound to carbons, and then double bound to another oxygen. And then these carbons have chains of carbons which are coated in hydrogens, and these chains will go on, and different oils differ from each other based on the number of carbons that they have in those chains. All right, another name for this kind of a compound is called a triglyceride, Now, you might look at this compound and say, hey, there's some oxygens there, and this must be a polar bond. Yeah, there is a degree of polarity there, that's right. However, with the sheer mass of these tails, these fatty acid tails coming up here, and with this non-polar group on top, these don't have the opportunity to contribute to any dipole-dipole interactions. Oils generally only will react with polar compounds, or sorry, non-polar compounds, or London forces. All right. One interesting thing, chemical property of, or a famous chemical reaction with oils. Let me draw this again. This time I'm going to just draw it quickly like this. Carbon, carbon, carbon. All right. This triglyceride is, what you normally find in the fat of animals, or in corn, or sorry, vegetable fat as well. And people realized early on that when they're cooking animals on the fire, a lot of the fat will burn off and kind of fall into the fire. And along with that, the wood that is there being burned results in some potassium hydroxide. That potassium hydroxide results from the wood being cooked there. And if you mix those ashes with the leftover fat from your animal that you're barbecuing or whatever, the oxygen here will actually attack this carbon and result in this molecule right there. And that molecule is a soap molecule. It has here on the end a polar head. But this polar head is attached to a non-polar tail. So this area right here, hold on just 1 second. What's up? This polar head here has the ability now to undergo some strong dipole-dipole interactions, maybe even some hydrogen bonding. But this tail here only can undergo London forces. It only interacts with other compounds through its London forces. And so this molecule becomes what we call a soap or a surfactant because I can use it to pull other hydrophobic or compounds that only respond to London forces. I can use it to pull them off of surfaces. Okay? Now, we're in the middle of this COVID-19 thing, and people are all excited about hand sanitizer. Now, hopefully you know that hand sanitizer works just as soap works just as effectively as hand sanitizer. There was a time where the soap companies got together. Well, one of them said, we're going to call our soap antimicrobial soap. Antimicrobial soap. And they did that, and people started buying that soap because they thought, we have to get the antimicrobial soap. We want soap that kills bacteria. Kills bacteria isn't the right word. It removes the bacteria off of the surface, right? And it can do that for viruses as well, or anything that has a hydrophobic shell, a shell that only responds to London forces, right? And so soap can do this on a molecular level and kind of a macroscopic level as well by forming what are called micelles. So we draw the soap molecule simplistically with a head and a tail. The tail here being the hydrophobic end, and the head there being the hydrophilic surface. Now these are words that we should make sure we all understand. Hydrophobic tail. Do you know what hydrophobic means, Chase or Jace?
Yeah, it means like water hating.
Okay, so
It doesn't react well with water.
that's right. It would repel water like oil would. Our hydrophobic tail, hydrophobic, and then our hydrophilic head, right? The hydrophilic head. Hydrophobic tail and the hydrophilic head. When we have a lot of this in water, now you might think this can't go into water because it has so much hydrophobic component, but it can because this hydrophilic head allows it to kind of protect the hydrophobic portion from the water. And what happens is, like we have drawn here in this structure here, I have all of these little purple soap molecules sticking their hydrophilic heads out towards the water. You can think of these purple things as the water. And the hydrophilic, did I say hydrophilic? I think I said hydrophilic heads out towards the water with the hydrophobic tails in towards the middle. Now this looks like a two-dimensional circle, but this is actually supposed to represent a three-dimensional sphere. All right, and this three-dimensional sphere is also what we see when we see bubbles, except for when we see bubbles, those are not just those are double layers. Those are films, right? But these films and these micelles are the strong component for their ability to clean a surface or to remove anything that's hydrophobic off of your hands. Okay, so you got a hand here, right? Just came in contact with something bad, doesn't know it's there, right? Needs to get it off. Why is it that bacteria or viruses stick to our hands? Because they're very hydrophobic. The same way, you know, if you ever tried to cook or clean food off of pans, if your hands get oily, you can't just wash your hands. It won't go away, right? If you want to get that oil off, you need to use soap to get it off. Same reason why bacteria or viruses will stick to your hands, but micelles formed from soap molecules are very good at removing other hydrophobic things from your hands. Okay? Soap by itself, you need to use the water to rinse it off, right? So you can use the soap to kind of interact with those hydrophobic material, bacteria, viruses, so forth, but you need the water to rinse it away. Okay? Hand sanitizer. Hand sanitizer is generally higher than 60% alcohol. There isn't a hydrophilic molecule like soap or a surfactant of any kind. It's just alcohol-based generally. And those alcohols dry up the surface of bacteria and or viruses and will cause those surfaces to unfold, the protein surfaces to unfold and to be non-viable, to kill them basically. Okay, so soap and hand sanitizer are different animals. They behave differently, and there's also you know, a variety of different, maybe 3 or 4 different kinds of hand sanitizers that work slightly different. Yeah, so interesting stuff there. Okay, what would we say? Which one of these would we not expect to be soluble in water, Landon? Which one would we expect not to be soluble in water?
So I know it needs to be hydrophobic, but I don't know. I'm struggling right now trying to understand what relates to the molecule being hydrophobic.
Okay.
Or what components of the molecule.
Okay, so let's do this. If it's like water, then we say it's hydro what?
Hydrophilic.
Philic. Okay? Hydrophilic is like water. Now, how is it like water? What are we saying? What part of it is like water? Well, it's its intermolecular forces. So it can do what?
It can interact.
It can interact with water. What kind of intermolecular forces does water have?
Sorry, I just blanked. It's...
So we can draw ourselves a water molecule to remind us, right?
Yeah, it's hydrogen bonding and dipole-dipole.
Very good. Hydrogen bonding, dipole, dipole. So if a material is going to be hydrophilic, it's going to either have hydrogen bonding or dipole-dipole. And hydrophilic compounds will be able to be soluble in water. Hydrophobic, that is, water-fearing, not like water. And how is it not like water? It's not like water because it doesn't have the same kinds of intermolecular forces. So it's not going to be hydrogen bonding. It's not going to be dipole-dipole. It's only going to be London dispersion forces, right? Does water have London dispersion forces, Landon?
It does.
It does, but why didn't we list it here as one of them?
Because it's not a main, I believe.
That's right. Compared to the amount of energy associated with the hydrogen bond, the London dispersion forces is very small. And water molecule is just a really small molecule in the first place, so it's going to be a very, very minimal amount of London forces because of its size. All right, so we're looking for a compound that has similar intermolecular forces as water. So what do you think here? You want to try it, Alyssa?
I'm sorry, can you repeat the question?
Well, we're just trying to find which of the following are not expected to be soluble in water.
Well, I feel like the CH4 would not be soluble because it only has hydrogen or the London bonds.
That's right. Very good. So HF is going to have high. What kind of intermolecular forces is HF going to have?
It has hydrogen bonds.
Yeah, hydrogen bonds. Very good. CH3OH.
I think does it have one hydrogen bond and then other polar bonds?
That's right. It does have hydrogen bonds as well, right? So we got CH3 and then OH. That bond to oxygen there will be able to hydrogen bond with a neighboring molecule of our CH3, OH, right? Whoops, hydrogen there. Okay, very good. All right, so let's see. I think this is a good place to stop for today. So we're going to stop here and then we'll have some more conversations about boiling points, heating curves, phase diagrams next time. Okay, so if you have any other questions, you can hang around and ask those questions. Otherwise, I will see you guys on Monday.